Okay, now in today's lesson, we will be doing Kirchhoff laws. In electricity, these are considered very basic laws, but these basic laws are driven from more fundamental laws in physics, and they are based on them, but they use more terminologies, terminologies, and concepts of electricity. Now, first of all, uh, law of conservation of charge. What is law of conservation of charge? That we cannot create or destroy charge. We can just make it go from one place to another place. We can uh, put energy on it. We can take energy from it. We can use electron to transfer electromagnetic energy. We can use electron to transfer mechanical energy, heat energy, and we can use electron to transfer electrical energy. But we cannot create or destroy electrons unless we make electron interact with a positron. That is a totally different concept in physics. So and that also holds on the law of conservation of charge, because the total charge even in that case stays same. Kirchhoff first law is based on law of conservation of charge. The law states total current that enters a junction is equal to total current that leaves that junction. Total amount of current that comes to a junction is equal to total current that leaves that particular junction. Because it is about current coming and leaving a junction, this law is also known as Kirchhoff junction law. Let's say P is a junction, different currents are coming and leaving P. Let's see which currents are approaching P. Using arrows, you can see I1, I3, and I4. They are all coming towards P. What currents are leaving P? I2, I5, and I6. So according to Kirchhoff law, total current that is coming, which is I1 plus I2 plus I3, sorry, I1 plus I3 plus I4, should be equal to total current that leaves, which is I2, I5, I6. So total current that is coming is I1, I3, I4. Total current that leaves is I2, I5, I6. So apply Kirchhoff law, total current coming equals to total current leaving. These kind of equations can help you to solve a problem. For example, if you know different currents that are coming, you can find out what currents are leaving, and then you can find out any missing current or any relationship between two missing currents. Now, Kirchhoff's second law is also based on a very basic law in physics, which is the law of conservation of energy. Law of conservation of energy is that we cannot create energy, we cannot destroy energy, we can only convert energy from one form to another form, but we cannot create or destroy energy. Kirchhoff's second law is based on, excuse me, a fundamental law or known as law of conservation of energy. Kirchhoff's second law states total EMF developed in a closed loop is equal to total potential difference in the same loop. By definition, EMF and potential difference are opposite concepts of same physical quantity. Opposite concept of same physical quantity. What do I mean by opposite concept of same physical quantity? EMF means how much energy has been converted from any other form of energy to electrical energy per unit charge. Whereas potential difference is amount of energy that has been converted from electrical energy to any other form of energy per unit charge. So in this law, because energy converted from other form to electrical in a loop is equal to energy converted from electrical to other form in the same loop, because we are saying loop more than once over here. So that means this is also known as loop law, Kirchhoff's loop law. Now, here we have a closed loop. A loop starts from a certain point and ends at the same point. For example, if this is a loop, we can say it is A, B, C, D, A, or we can say it is D, C, B, A, D. Like you start from a point, and if you can come back to the same point following any route, that means we are talking about a closed loop. So A, B, C, D, A. Now, there are two EMFs over here, E1 and E2. There are three external resistors, R1, R2, R3, capital R1, capital R2, capital R3, and there are two internal resistances, R1 and R2. Loss volts, two loss volts, IR1, IR2. Three potential differences, IR1 with capital R, IR2 with capital R, and IR3 with capital R. So there are altogether five potential differences, two internals and three externals. There are two EMFs. And when we look at the EMFs, they are trying to produce current in the same direction. So they are actually in the favor of one another. So total EMF produced in this loop will be E1 plus E2. And this is because they both are producing EMF in the same direction. They're supporting one another. They will set current in the same direction. If they would have their terminals in the, like one of them would have their terminals in the opposite way, then it would be E1 minus E2 or E2 minus E1. Okay, now it is E1 plus E2 in this case, which is total EMF developed, and total potential difference will be IR1, IR2 plus IR1 plus IR2 plus IR3. So you see, when we will be applying these things in a question, they will make more sense. But this is how we can make equations, and at your level, examiner can only ask you to make equations. In later classes, when you will be studying this topic in university, you will find out that we can set many equations, and we will end up with a, in a complex circuit, we will end up with a very complex equation system. And by solving that equation system, we can find out different currents. And in that, at that level, you might ask to solve that equation system. At this level, we just have to make like just show that an equation can exist over there. Okay, so you can see that total EMF is E1 plus E2. Total potential differences are IR1 plus IR2 plus IR1 plus IR2 plus IR3. So this is how this whole equation is established. Let's see, we have some questions like this over here. Kirchhoff law questions. Oh, here we have Kirchhoff law, purely Kirchhoff law question. You have this question in the PDF that I have shared with you. So you can open this question and see if you can solve it by yourself. Okay. Three cells of electromotive forces E1, E2, E3 are connected into circuit, and we have this circuit over here. The circuit contains resistors R1, R2, R3, R4, and luckily there are no internal resistances in this case. Now, use Kirchhoff law to state an equation relating I1, I2, I3. Look for any junction where you can see these three currents getting together or getting separated from. Look, if I consider W, if I consider this as a junction, what currents are coming to this junction? Look at
I2, I2 and I1.
I1 and I2, they both are coming to the junction. Which current is leaving W?
I3.
Okay. Can we set a relationship between these three now?
Yes, sir. I1 plus I2 equals I3.
Good. I1 plus I2 equals to I3. Good. Now, E1, E3, R1, R3, R4, I1 and I3 in loop W, X, Y, Z, W. W, X, Y, Z, W. So it is asking for the rectangular circuit over there. Not the triangular part, but the rectangular part. So when current goes like this, it loses, and there's a potential difference of minus IRC. We go from a lower potential to a higher potential of the EMF. It is a plus E3. We go like this, it will be I3R4. There will be a loss of potential difference. Current goes like this, it will be I1 R1. When we go like this, that will be plus E1, and then there is no more change. So let's see, what do we have over here? It is minus I3R3 plus E3 minus I3R4 minus I1 R1 plus E1 equal to 0. So this is one way of solving this one. And you could do the other one as well. What is total EMF produced? You can see E1 and E3. So you could do this one. E1 plus E3 equals to total potential difference would be I3R3, I3R4 plus I1 R1. And how many of you can see that both of these equations are same?
Yes, sir, it's the same.
In the upper one, uh, all of the terms are written on the same side of equal sign and there is a zero on the other side. And although I made both of the equations with two different approaches, like found total EMF and then I found potential difference, I put them equal, or I went along the circuit, along the loop, keep adding the areas where the potential was increasing and keep subtracting where the potential was decreasing. And I got the same equation. Let's see. Uh, y z w y y z w y. I will recommend that you should give it a try. Because in a case of opposite EMFs, E1 and E2 are not in favor of one another. See, if you go like this, there will be a loss of I1 R1, gain of E1. We are now going opposite to the direction of current. So it will be plus I2 R2. And when we go like this, it will be minus E2 and we reach Y. So total potential, total EMF in this case will be E1 minus E2 equals to, or I could do like this, minus I1 R1 plus E1 plus I2 R2 minus E2 equal to 0. So it can become E1 minus E2 equals to I1 R1 minus I2 R2. So it is a 1 mark question of like for each equation, and this is how this question comes. You don't have to do anything further or anything less than this one. Let's see if we can solve one more question.
Then after the completion of syllabus, will the classes end or will we do past paper?
We will do kind of crash course kind of revision, and yes, we will be doing more past papers then.
Right.
Okay, we still have time today, so we can solve some questions. Let's start with this one. State what is meant by an electric current. Electric current means flow of charge. Electric current means moving charge. Define electric potential difference. difference of electrical energy per unit charge difference of electrical energy per unit charge between 2 points is called potential difference. The power supply of electromotive force EMF 8.7 volt and negligible internal resistance. This is very important to know. So we do not have any internal resistance in this case. Now, current of 0.30 ampere is set in the, and we have long connecting wires. I haven't read the question yet, but I can see if he has intentionally made the wire so long that he will definitely have some part related to that, these wires will offer some kind of resistance for them. The power supply provides a current of 0.30 ampere to circuit. The filament lamps are identical, and these are the characteristics of each one of them. So when potential difference is increasing, current is increasing. Show that the resistance of each connecting wire. See, this is what I was talking about. He's asking for the resistance of each wire. Very easy. Each lamp is having a current of 0.3 ampere. Go to 0.3 ampere on the graph and look at the potential difference on the other side. So what is this value?
2.5.
So it means that each lamp is having 2.5 volt. 2.5 volt, 2.5 volt, 2.5 volt. Together, this makes
7.5.
And how much is the power supply providing?
8.7.
8.7 volt. It means remaining voltage is consumed by each wire.
1.2.
1.2 volt altogether. So 0.6 volt for this one and 0.6 volt for this one. Question is each one having resistance. So if I know potential difference and I know current for each wire, potential difference is 0.60 volt. Confusion?
No, sir.
Good. But this is how we have to solve this kind of question, that we first find what we know, and by finding the difference between what we know and what we don't know, we can find out the missing part. The resistivity of the metal of the connecting wire does not vary with temperature. Okay, he's saying that for this particular experiment, that in this case, the resistivity is fixed. On figure 5.2, sketch a IV characteristic for one of the connecting wires. Okay, so When they have a current of 0.3 volt, their potential difference is 0.6 volt, which is like here. So there should be a line like this. There we go. So there should be a straight line because this is a filament lamp. This one is filament lamp. Resistance increases with temperature. But the metal wires that we use, their resistance is not increasing. So it should be a straight line and passing through point 0.06 and 0.3. Because when there is a potential difference of 0.6, there is a current of 0.3 ampere. So, okay, 2 marks just to draw that easy. Calculate the power loss in one of the connecting wires. Power equals to voltage into current. So 0.60 multiplied by 0.30 should be 0.18 watt. Now, some data for the cross connecting wires is given. Cross-sectional area is given, resistivity is given, number density of free electrons is given, that's the length of the connecting wire. The formula that connects all these things is the resistance equals to resistivity L over area. So L equals to the resistance area over resistivity. So 2.0 multiplied by area is 0.40 into 10 to the power -6. Remember, milli is 10 to the power -3, but there is a square on it. 10 to the power -3 square is 10 to the power -6. Divided by resistivity 1.7 into 10 to the power -8.
47.06 meters.
40,
47.06 meters.
47.1. So 47 meters. Can someone else confirm? Uh, 80 divided by 1.7. Okay. Yes. Now, drift speed. What is the formula for drift speed? V equals to I over A N E. I was 0.30. Area is 0.40 into 10 to the power -6 multiplied by n. Number density is 8.5 into 10 to the power 28. And elementary charge is 1.6 into 10 to the power -19. So what do we have? Minus 19, minus 6, minus 25, 10 to the power 3. Three divided by 4 divided by 1.6 divided by 8.5, 0.55.
And 5.5 meter per second.
5.5?
Yes.
Are you sure? Can somebody confirm? Because I'm
Yes,
getting
sir. 5.5.
okay. I'm getting a far lower than that. I'm getting 5.5 into 10 to the power minus 5 meters per second. Pata nahi kyun. Okay, just check it with the calculator. Minus 6 minus 19 is minus 25 plus 10 to the power 3 is in the
सर
denominator.
मुझे भी 5.5 into 10 to the power minus 5 है
10 to the power minus 5 आ रहा है आपका सर?
जी मेरा आ रहा है
Soban, just replicate the whole calculation in your calculator in one go. Do not do any stepwise calculation. Can you put everything in calculator in one go? Hello? Okay, then final answer will be 5.5 into 10 to the power minus 5 meters per second. You can confirm it from the marking scheme as well, if you want to. And there are lot of questions. You should practice them. And tomorrow we can have a class for, let's say, first 6 questions. First 6 unsolved questions. Okay. Try to solve these questions at home, and tomorrow we can discuss them. Okay.
Okay, sir.
at the same
Okay,
time
sir.
sir?
See you people tomorrow. All the office.